Good morning, everyone. Today I'm excited to talk about resolving smarter, not harder, performance gains via query aware filtering. This is a joint work with Liz from UCLA, who was my mentor during the fellowship, and Yelena from USCISI, who is my PhD advisor. So, what is the DNS? DNS is domain name system. It is generally called the phone book of the internet. It is responsible for translating human readable domain names into IP addresses. And we are aware that it is organized hierarchical in nature, meaning there is no single entity which controls or is responsible for resolving the whole name. To make sure all of us are familiar, we can quickly run through how DNS works. Let's say a user device wants to visit www.foo.com, but it does not know the IP address of foo.com. So it contacts something known as a recursive resolver, which is usually present at an org level or at an ISP level. And let's assume that this recursive resolver has a cold cache, meaning it has no entries for any of the labels in the domain. So the recursive resolver would first go to the root server, which is at the top of the hierarchy, ask the root server, what is the IP address of foo.com? However, the root server would not know this. So it will tell the recursive resolver to go to the TLD server, which is the .com server in this case. The .com server wouldn't know this either. Again, it would tell the TLD server to go to one of the authoritative name servers. Finally, the recursive resolver will get an IP address for foo.com. This IP address, the recursive resolver will add to its cache and then give it to the the client, and the user is finally happy. All of this looks perfect, right? What is the problem? Why do we need research on this? That is not the case. Since DNS inception for more than 35 years, there have been past research from 1992, which has quantified that more than 70% of queries that come to root servers are junk. These queries are called junk because they do not meaningfully contribute to the larger DNS ecosystem. These queries are broadly classified into queries for non-existing TLDs, meaning there are about 1,500 valid TLDs today. And query with TLD that is not among that list is a query to a non-existing TLD. Next category of junk queries is repetitive queries, wherein a query to the same existing TLD before the time to live, TTL, expires is also not meaningfully contributing because the recursive resolver is expected to cache that. And these junk queries have been used in the past for a lot of DDoS attacks on critical infrastructure. Froot server itself, which is one of the 13 root servers, DNS root servers in the world, was attacked in 2002. 6 of the 13 root servers faced a DDoS attack in 2006. All the 13 root servers, along with the famous DIN attack in 2016, is another example. Junk queries are also used by botnets and command and control systems. And prior research has quantified the impact of performance and the results and poor user experience due to attacks by botnets and CNC systems. So what is our proposition? We are proposing to have an enhanced resolver which can make decisions locally, meaning you can have additional capability at your recursive resolver and decide if you want to send a query out to the larger DNS ecosystem or not. We do this by having 3 different sub approaches. One is to validate the TLD. And if the TLD is valid, only then you send the query to the larger DNS ecosystem. Otherwise, you can respond to the user device with an NX domain locally. Next is rate limiting. Say every recursive resolver has an ability to quantify the number of times a query with the same domain name and a TLD can be treated as okay. And when the number of times that query is repeated exceeds the threshold, it is called repetitive, and then it can rate limit the user. The third one is response policy zone, RPZ for special cases. I'll talk more about it later. So with our experimentation, we have found that this approach is most effective for reducing or filtering queries that go to the root server in particular. This figure is an enhancement of what was there in the previous one, which we called baseline, and this is the enhanced resolver. So we have 3 functionalities, as I said. For the first query for foo.com, the recursive resolver, if it has a cold cache, it will just send it out to the DNS ecosystem. For the second one, for bar.com, if that query is repeating n number of times, and assuming n is higher than the threshold, the resolver has an ability to rate limit the client. And the third one is just junk. It is something I typed up on my keyboard randomly. The algorithm on the right is a high-level overview of how we make this decision locally. So it's about 11 lines of addition to a baseline resolver. And we begin with fetching a list of TLDs from IANA's website. IANA is the authoritative server or authoritative source which provides what are the list of valid TLDs. We do this every 24 hours. And prior research has shown that TLDs and IP addresses to TLDs remain fairly consistent over more than 24-hour period. So we find 24 hours to be a good match in this case. If we validate the TLD, as I mentioned before, and if it is not an existing TLD, we just return an NX domain. Regarding RPZs, as I mentioned, one example is Chromium-based queries. So Chromium is a web browser project that was developed by Chrome in the late 2000s. This project aimed at determining if there is a captive portal present between a user client and the server that is responding to queries. So Chromium generated 3 random queries using randomly picked alphabets, which were of specific length between 7 to 15 characters, all in lower cases. And if 2 of those responses got the same IP address back, then Chromium determined that there was a captive portal. We can use a similar approach in configuring the RPZs and then make sure if the query is matching the pattern of 17 to 15 lowercase characters, we can respond to both those queries or even all the 3 queries with the same IP address. RPZs can also be configured to handle split horizon DNS specifications. We experimented with some of it and it works well. Next up, to evaluate how our approach worked, we implemented both a baseline resolver and an enhanced resolver. The enhanced resolver is about 6-7 lines of additions. And we implemented both of them using Unbound 1.23 and experimented them on Spear, which is a cybersecurity experimentation testbed. In order to emulate real-world data, we downsampled queries that we got from broot server. It is one of the 13 root servers which participates in the Day in the Life of Internet collection. This data is from 2025. And we evaluated both basic and enhanced resolver and collected and compared metrics. We focused on metrics such as memory consumption, latency, and CPU utilization. The algorithm on the right is a high-level overview of how we do this. So what did we find? Was it interesting enough? Yes. The figures on the right, both of them have x-axis for elapsed time in seconds. The figure A for CPU usage has y-axis for CPU in percentage, CPU utilization in percentage, and the latency figure has average latency in milliseconds on y-axis. And the red is for basic resolver, green is for enhanced resolver. So during the 1 hour time period that we emulated both the resolvers with real-world queries, we fed them with about 355,000 queries and found that enhanced resolver operated at about 10% of CPU utilization in comparison with the baseline resolver, which was at about 18%. This is a 44% decrease in CPU usage. Similarly, for latency, it was about 13 milliseconds in the enhanced resolver case, while 30 milliseconds in the baseline resolver case. That is about 55% reduction in latency. In order to also evaluate how a specific resolver would perform in cases when only one category of queries was fed as input, we experimented with 3 different scenarios. The figure on the right has elapsed time in seconds on x-axis, and all the 3 of them have CPU utilization in percentage on y-axis. Again, red is for basic resolver, green is for enhanced resolver. So the non-existing TLD case is when we fed both the resolvers with 355,000 queries, where all of them just had non-existing TLDs. And we noted that there was a 68% reduction in CPU usage. And from figure 1, the sub-figure A for non-existing TLDs, we can also note that enhanced resolver finished completing or resolving all the queries much sooner in comparison with the baseline resolver. For repetitive queries, it was a similar case. It was about 42% reduction in CPU utilization, while for legitimate queries, they were identical in both cases. However, not everything was well. We observed a 50% increase in memory overhead. We operated this under a /16 network with about 65,536 clients. The enhanced resolver stood at about 36 megabytes of memory consumption and the baseline resolver at 24 megabytes. It is important to note that this memory does not include memory required for DNS caching. We would also like to note that given the capacity of modern resolvers, this is not a significant increase in memory consumption. To calculate memory overhead, we use this formula. So M0 is the baseline memory, which is 24 megabytes in our case. C is the number of clients. Since we operated in a /16 network, C naught would be 65,536. T is the number of TLDs. And for our baseline case, we just rounded off TLDs to 1,500. As of today, it is less than 1,500, but we are expecting the TLDs to grow in the next round of GTLDs upcoming in 2026. So we found a memory consumption of about 200 bytes to store the metadata for each client in our case. As we can see from the formula, this memory consumption is proportional to the number of clients and the number of clients a resolver is serving in a network, and also the number of TLDs. So how is this beneficial in comparison with what has already been done? So our approach does not require changes to the DNS architecture as opposed to what has been proposed in the past. RFC 8806 proposes the utilization or a move from a root server system to having a local copy of the root server on your resolvers and then not at all talking to the root servers. There have been more radical propositions, such as moving DNS to a peer-to-peer network instead of hierarchical as it is today. And there was one other approach which suggested complete elimination of the root server system at all. However, our approach is implementable using open DNS software. We experimented with Unbound and we believe it is expandable to others as well. Also, the proposition that we have is deployed at a resolver, but its benefits expand to other hierarchies in the DNS ecosystem. Root servers would receive only about 24.34% of queries in comparison with what they see today. Today, they receive more than 7 billion queries every day. If our proposition was implemented ideally at every resolver that is present in the world, it would just have 1.8 billion queries. But ideality never exists, so we will still see queries. For recursive and forwarding resolvers, they are the natural beneficiaries. We would see a reduced CPU load and latency. And this would also help clients and end users with an enhanced quality of experience. One major limitation of our experimentation is that all our experiments were performed in controlled environments using synthetic workloads. Although we used B-root servers downsample data, we believe that doesn't fully capture the diversity and the unpredictability that is present in the real-world DNS. And DNS can go wild, as we have already seen in the past. All our results are based on implementation in Unbound 1.23. However, prior research has shown that implementations can vary based on open source software. Although this is generalizable, we believe if this approach is implemented using bind or not, there would be some changes in the performance that we observe. And we quantified memory overhead, but we never tried to optimize it. We quantified memory overhead for per source per TLD base. As one might already predict from the formula that we saw before, memory consumption would grow larger if we did it for per source per domain pair. So in conclusion, DNS has a lot of junk queries even today. In order to deal with this, we propose a lightweight source-aware query filtering mechanism. This mechanism, when implemented at a resolver, it would significantly reduce CPU usage by more than 44% and also reduce latency by more than 55%, with a minimal overhead of about 12 megabytes per /16 network of about 66,000 clients, which is manageable in modern day resolvers. I would like to take this opportunity to thank Internet Society Pulse for providing me an opportunity to work on this research through the fellowship. And with that, I'll be happy to take any questions.
So this is super interesting. Thank you. But one of the, so there's a two-pronged question. So for your solution to work, it needs to really be implemented on every recursive resolver on the internet, which if you follow one of the trouser legs, let's say, everyone is using Cloudflare and Google. So that's easy to implement. Google and Cloudflare need to implement it and we're done here. There's no more junk traffic to the internet. If we follow the other trouser leg, which I think is much more interesting, is every single network runs its own recursive resolvers, or ought to run its own recursive resolvers. A network can be many different things. So an ISP network, service provider networks, usually have a cluster of DNS servers. So you're asking every ISP on the planet to go and implement your solution on their DNS clusters. That feels like a lot of work, but still manageable. But on the very, very long tail of the recursive resolvers are all these little domestic modem-y things, which we've all got sitting in our living room, kitchen cabinet, which all have a firmware on them, which nobody ever upgrades in the wild. Do you have any sort of way of quantifying how well your solution can work in the real world? Did you study where the resolvers are and realistically how many of them can implement your solution?
Yeah, that's an interesting question. So one of the research that I'm currently working on is trying to understand the sources of such queries. And in that, we have found about 18% of large contributors that exist are responsible for at least 85% of traffic that come to the root servers. So if this solution is implemented on all those 18%, and these are from major companies such as Google, Cloudflare, Amazon, among others. So if this solution is ideally implemented at just 18% of those resolvers, we would still get rid of ideally 85% of queries that come to the root servers.
Okay. Any other questions?
Actually, it's not a question, but we'll say something against his comment. Sorry. I think this is the kind of thing that provides incremental benefits. The more you deploy this, the better return you get. So it's perfect. Perfect. But it's, sorry, exaggerated. Yeah. Yeah, I want to sell the stuff. Well, it doesn't require wide adoption to provide benefits, right? It provides benefit as you go. Day zero. What can you expect more? Honestly.
So quickly to respond to that, what we need to expect more is I think we need more real world experimentation with this, because most of our experiments were in like controlled environments, and those milliseconds we see for 30, 35 milliseconds that is never true in the real world DNS, right? So we need to understand how much of a difference it is. Is it still 55% decrease in latency when we deploy it? And it would also depend on other factors, right? So we have not taken that into consideration, but I think this is like a starting point for one organization who is like interested in collaborating, working with us, and then seeing if it works well for them. It might work for other organizations of similar capacity.
Thank you. Yeah, one more question.
Thank you, Dipsy, for your presentation. So this is something we discussed already. It is about the reaction that you got from root server operators. As context, Paul Hoffman looked at his blog post and then said, why is there a need actually to do this work? Because there is no problem of resiliency for root servers. What would be your response to that?
Yeah, I think that was an interesting conversation. For the past more than 30 years, we all know that there is a problem. It's just that I feel we have been adapting to that problem. Every time there was an increase in number of unwanted queries or unexpected or junk queries, we have just increased our capacity for root servers or TLD servers or any other authoritative name servers. So instead of doing that, we can come up with a solution where we finally try to put an end to the junk queries that appear, and maybe come up with mechanisms where we can prevent future junk queries from even appearing in the DNS ecosystem. So I think it's still a debate that is ongoing if we want to do this or not. But we believe this is a good approach, being on the right side, that we want to reduce something rather than trying to adapt to the problem that exists and increasing our capacity over time.
Okay, thank you very much, Dipsy. Oh, one more question. Okay.
Just wondering if there's any negative point here. I think you said something about there being a 24-hour cache that you use. So if I create a new DNS for the first 24 hours, and if it looks like a junk DNS, does that mean that I'm unreachable when Google and Cloudflare implement this?
So do you mean 24-hour cache for the IANA list of TLDs?
Yeah.
So IANA list of TLDs, I think IANA maintains them. And if something is changed there, if we implement this solution, then we would only realize in the next 24-hour period. But we also experimented with a 1-hour period instead of 24 hours. But we could not find sources which like said what was the capacity of the IANA server where we can like query it frequently, because I'm assuming there are more than millions of resolvers in the world today. And if each of them sends a query to IANA's website every hour, we don't know how it is going to impact. So if there is some source that can say IANA servers are resilient enough for a billion queries every hour, then we might even reduce it from 24 hours to 1 hour.
In your server filtering, like the second one, you look at the TLD and X domain errors, but I'm surprised to see a lot of errors with the TLD. Oh, okay, with subdomains, attackers use like subdomains, but like you mean invalid TLD?
Yeah, a lot of them appear because of invalid TLDs. It is just that something random pops up, and we don't even care about the subdomains here, SLDs. It is just about the TLDs. And I think it is at least 38% for all years of digital data that we observe. Queries with non-existing TLDs are there. Yeah, that's, I think, 4 billion every day or something.